Okay, so we are working on 6.7. We're going to deal with a similarity transformation. We've spent some time on congruent transformations with reflections, rotations, and translations. And now we're going to work with dilations. So a dilation is a transformation that will stretch or shrink to create a similar figure. Obviously, when we were doing congruent transformations, the two shapes had to stay congruent. But now we can change the size, either larger or smaller, because we're dealing with similar figures instead of congruent. The center of dilation is the fixed point about which the transformation takes place. Sort of like when we were doing reflections. We will always use the origin. We're going to do all of our transformations on coordinate planes, which is why we're using the note-taking guide again, and the fixed point will always be the origin. The scale factor of the dilation, we mathematicians agree to use k for scale factor, kind of like m for slope, and k is scale factor. The scale factor is the ratio of side length of the image to the side length of the original. So it's the ratio of the side length of the image to the side length of the original. It's really important that you have the fact that it's from the image to the original. Because obviously a scale factor of 1 to 2 is different than a scale factor of 2 to 1. Now, the dilation can be bigger or smaller, and so within dilations you have sometimes your images are going to get smaller, and that's a reduction, and sometimes your images are going to get larger, and that's an enlargement. So one way to know ahead of time is that if the scale factor is less than 1, and we won't be dealing with any negatives anyway, but if the scale factor is between 0 and 1, you're going to have a reduction. It's going to shrink or get smaller. Okay? If the scale factor is greater than 1, that's when you have an enlargement, and so that's when it stretches or it gets larger. Okay? Obviously, if you have a scale factor of 1, it doesn't change at all. So that's why it has to be less than 1 or greater than 1. So we're going to talk about coordinate notation for a dilation. You can describe a dilation with respect to the origin. Again, that's our fixed point. With the notation, for every point xy, if you multiply the x by the scale factor and the y by the scale factor, that's where you'll get your new point. So this is just reiterating that if it's between 0 and 1, you're going to have a reduction. And if it's greater than 1, you're going to have an enlargement. Okay? All right. Now I've taken the liberty of I've already gone ahead and plotted the first 4 points in our first example. So we have draw a dilation of quadrilateral ABCD with the following vertices, and I've plotted that. It says here, use a scale factor of 1/2. So in this case, they're not asking you what the scale factor is. They're coming out and saying, we want you to use a scale factor of 1/2. So we're going to first draw the shape, the quadrilateral ABCD, and we're going to find the new points by multiplying by 1/2. So just like we were looking at the coordinate notation, you take every point, xy, and you're going to multiply 1/2 times x, and you're going to multiply 1/2 times y. Now I know that this was originally labeled different points. They labeled them L, M, N, and P. I get a little frustrated with your book doing that. Most books that I've seen talk about the image of point A is A prime, like we talked about before. The image of point B is B prime, C prime, and D prime. So excuse me. That's what I'd like you to change these to. Instead of calling them something completely different, I'd rather have us create a new quadrilateral that would be A prime, B prime, C prime, D prime. So literally all we're going to do is we're going to take point A and we're going to multiply the x by a half and the y by a half. And that's A prime. And then same thing for this. Half of 6 is 3. Half of -4 is -2. And we're going to continue on. And now we have those points that we're just going to, literally we're just going to plot them. I might switch to a different color. You don't have to if you don't want to. So A prime is going to be the point 1, 0. And I'll label it when I'm done so that I know where things fit. B prime is going to be the point 3, -2. Now I can see where they're going to fit. And C prime is 4, 1. And D prime is going to be 3, 2. And you can use a ruler if you'd like to save time. I used a ruler for the big one, but this is small enough that I'm just going to go ahead and connect them. Now clearly you can see my original in purple is larger than my image, so this would be a reduction. I would have known that already because I can see that the scale factor is less than 1. So even before I started drawing anything, I knew that I was going to shrink this image, that it was going to be a reduction. Okay, let's go ahead and take example 2. Again, I've drawn in the original 3 points for triangle ABC. This time we're going to do a scale factor of 2. So the directions are to sketch both of them and to verify that they are indeed similar. So the scale factor is greater than 1, so we're going to expect this to be an enlargement. And since the scale factor is 2, literally I'm just going to multiply each coordinate by 2. So A prime is going to become 4, -2, and B prime is going to become 8, -2, and C prime is going to become 8, 4. And I'm going to go ahead and switch colors and graph this. 4, -2, which is going to go here. It's kind of in my way of B, but that's okay. There's my A prime, and then 8, -2, and then 8, 4. So we expected it to get larger. Okay, so my original is purple, my image is green. It has indeed gotten larger, and it's an enlargement. Now, we plotted both. That was part A. The next part says verify that they're similar. So we're going to say that because angle B and angle B prime are both right angles, then obviously we know that they're congruent. So angle B is congruent to angle B prime. Careful to make sure you can see the prime. Show that the lengths of the sides that include angle B and angle B prime are proportional. So in other words, we're going to be working with SAS similar here. So here's my right angles, and so I'm going to definitely use BC and B prime C prime. Okay, sorry for the phone call. We have our right angles, and so we have to make sure we use the sides that make up those angles. So we want the angle to be the included side. So if we're going to talk about AB, we're going to compare that to A prime B prime. And if we're going to talk about BC, we're going to compare that to B prime C prime. And we can, because they're vertical and horizontal lines, we can just count. Of course, we could use distance formula and Pythagorean theorem in this case, all kinds of different ways to get AC. But luckily, we can just count. We've got 2 units here for AB and 4 units here for A prime B prime. And we have 1, 2, 3 units here for BC, and hopefully 6. 5, 6, absolutely. And so obviously 1 to 2 is equal to 3 to 6. If you reduce that ratio, it's a ratio of 1 to 2. So the lengths are proportional, so the triangles are similar by SAS, similar. Okay. In example 3, it talks about that we're going to make our own photomagnets. That's cool. We're going to start with a picture that's 8 by 10, and the image of the magnet is going to end up being 2.8 inches by 3.5 inches. So the question is, in this case, what's the scale factor? Instead of them saying the scale factor is, they're saying what's the scale factor. So the scale factor is the ratio of a side length of the image to the side length. Okay, so I'm going to write the magnet image to the side length of the original photo. Okay, so we know that that dimension of 8 inches, the original, is going to go down to 2.8 inches. So that's what I'm going to put in here. Our ratio is 2.8 to 8. And if we reduce that, let's come over here and review a little bit how we deal with decimals and fractions. If I want to get rid of that decimal, I'm going to multiply the numerator by 10, and if I multiply the numerator by 10, I better multiply the denominator by 10. And then I can just reduce that, and we're going to get 7 over 20. So I don't have to do the other one, but you could confirm that 3.5 to 10 would also simplify to 7/20. So it would be 35 over 100, and then when you divide, you'd get 7 over 20. So that's good. All right, so at this point, the checkpoint is where you try this on your own. So at this point, I'd like you to pause the video and try those two on your own. So hopefully you've paused long enough to give this a try. I have problems 1 and 2 done. I drew the original. My black is the original, and then I was finding the coordinates so that we have a scale factor of 4. So literally all I had to do was take each coordinate and multiply by 4. -1 times 4 is -4, 0 times 4 is 0, 1 times 4, and so on. So I just took B, C, and D and came up with B prime, C prime, D prime, and drew those in. For example 2, what's the scale factor of the reduction if your photo was to start with 4 by 5? Okay, so if you started with a 4 by 5, again, you want to go with the, it's going to be the ratio of the image to the original. That's really important that you have the image to the original. So our magnet image, the second thing we're going to make is 2.8, and the original is 4. And I did the same thing, multiplied by 10 over 10, and then simplified to get 7 to 10. So my scale factor is 7 to 10. Okay, now our last page. Our last page, they drew this 1, 2, 3 quadrilateral, and they drew part of the new quadrilateral, and they're asking you where would the last point be based on what you have here. Okay, so determine if JKLM is a dilation of PQRS by checking whether the same scale factor is used. So that's one of the first things to do. So the first thing I want to do is just write down point P is 0, 3. I'm literally just looking where is it plotted. Point Q is 2, 2. Point R is 2, 0. And then to get point J, I'm looking at where that is, and that's 0, 6, and 4, 4, and 4, 0. So literally all I did was fill in the coordinates of what was drawn on here. Now I'm going to look and see, did they do the same thing every time? Well, to get from 0 to 0, it's hard to tell, but to get from 3 to 6, you have to double it. 2 to 4 is double, 2 to 4 is double. So the scale factor in all 3 cases is 2. So yes, indeed, we're dealing with some similar figures. Because K is the same in each case, the image is a dilation. In fact, we're going to enlarge it with a scale factor of 2. So you can use the scale factor to find the image of point M. So point S is 5, 5. And we're literally going to do 2 times 5 and 2 times 5 to get 10, 10. So that's all there is to that. All right, last time, I'd like you to pause the video for the checkpoint. Okay, and I've also done the problem. In this case, again, we have another quadrilateral with 3 of the points drawn in, and where should the 4th one go? So it's just like example 4. So literally what I did was I wrote down points W, X, and Y, and points Q, R, and S. And I noticed, and it's a little bit more tricky, it's not quite as obvious. No, we're not doubling it or cutting it in half or anything that easy. But if I were to take 2, to get from 2 to 5, let's come over here and show you. 2 over 1 times what is going to get me 5 over 1. And that's what I was thinking in my head. And so what I would need is for the 2's to cancel and have 5. So 2 times 5 halves is 5. And that's all of these cases. So the scale factor is 5 halves. And so literally that's all you have to do. We know we want to find point T based off of point Z. Again, I wish they said Z prime, but that's okay. So point Z is at 4, 6, and I literally took 4 times 5 halves and 6 times 5 halves. The 2 and the 4 will cancel and give me a 10. The 6 and the 2 will cancel and give me a 15. Okay, hope that helped.